The battery's on 2 things out of 3, so we're looking good.
Okay, so we're gonna have a little chat about energy because some of you guys have been asking about energy. So these are the energy type equations that come up on your formula sheet, and the type of the technique we're using when we're using energy. What's the kind of overarching rule that we know for energy? Always.
It's conserved.
Energy is conserved. That means that the total amount of energy in a system is always going to stay the same. So the way we use energy to solve problems is we hold on to that idea that the total energy must be the same. And that's an idea that we're gonna have to stretch a little bit when we move on to our next topic of nuclear physics, because we've got that E equals mc squared equation. We kind of have to allow mass to turn into energy and energy to turn into mass, and then we have to kind of come to a place where mass and energy are the same thing. Maybe we can let mass energy be constant. But anyway, energy is always conserved, and so we have to make assumptions about energy. What sort of things do we have to assume to keep energy conserved?
Air resistance is negligible.
Things like air resistance is negligible. Things like no energy loss to heat. Particularly the heat, because the heat is. Sorry, never apologise. Because heat's what we get from friction. So if we're assuming there's no heat losses, then we're assuming that friction is negligible. And so which of these equations are we familiar with already? Who can tell me something about some of these?
Third one.
Third one. What's the third one?
Don't know.
No, okay. Which one did you tell me?
First one.
John?
Kinetic energy.
What do we know about that?
Energy of things in motion.
Cool. So kinetic energy is the energy that something has because of its motion. Cool. So we call it usually, and that's due to how high we've lifted it up inside a gravitational field.
The last one is
What?
Work.
force times distance.
And the dot tells us that the force and the distance need to be same direction. Good. What is work?
Like the amount of energy put into doing something. That's where you're wrong. Yeah. The amount of energy that's transferring something. It's used over a distance.
It's the amount of force used
I
over distance.
know.
No. The amount of energy that's transformed from one form into another.
That's what it's...
And so then, if we come back to energy, what is energy? A nice
ATP.
way of thinking about it is the ability to do work. So if you've got lots of kinetic energy, like if you're a car driving along and you hit a concrete block, you've got a lot of ability to do work on that concrete block, to push that concrete block, to move it. If you lift something up in the air and then drop it, it's going to gain kinetic energy as it falls. It's going to gain the ability to do work. And so a nice way of thinking about energy is the ability of a body to do work. And then there's that other one. That's the new one for this year. EP. What do we know about it from the P? It must be
energy.
Just potential.
So
Must
it's
be
just another way
something.
of calculating potential energy.
It must be potential energy because it's got the P, right? Shit. Potential energy. Elastic potential energy. So elastic potential energy, we're talking about the kind of energy that you store in something when you stretch it or bend it. Like, as you apply a force, you have to apply more and more and more force as you pull back, I don't know, a rubber band ready to flick it at your friend. And as you pull it back further and further, you're storing more and more energy. When you let it go, that potential energy turns into
Kinetic energy.
kinetic energy. And so it's similar to gravitational in that we're storing energy, ready to release it, but we're not storing it in a gravitational field, we're storing it in an object by deforming that object, like stretching it or compressing it or something. So elastic potential energy, and K is the stretchiness. It's the spring constant. How do we measure it? We measure how many
Centimetres
newtons
per
we
newton.
need to stretch it or compress it by 1 metre. So K so newtons per metre. And the X then must be
Distance.
Unknown.
the distance
This.
stretched.
When in doubt, say displacement.
X is the distance stretched or compressed.